Welcome back to our course on memory device technology for AI/ML computing. I'm your instructor, Dr. Shubhadeep. Let's try to recall what we were studying the last time around. We saw that there are big bandwidth mismatches between the CPU and the memory. So the CPU works at roughly 3 gigahertz or more, whereas the main memory, which constitutes of DRAM subsystem, works at only 800 megahertz. And this mismatch is what is known as the memory wall. And to address this mismatch, there were some very interesting innovations that we do at the DRAM subsystem hierarchy in the form of this inverse pyramid. Okay, I understand this is a very, very new concept for all of us. So I thought it would be worthwhile to recap this entire concept with a slightly different perspective, and because this is such a new and innovative concept and very important for addressing the memory wall, let's have a relook at it once again. So in the previous class, what we did was we started from the bottom of the hierarchy. We started from the memory array and slowly we moved upwards to bank, chip, rank, DIMM, so on and so forth. But in today's recap, let's start from the top of the memory hierarchy, which is the processor subsystem. So what I have essentially done is I have first drawn the processor subsystem for you. So as you know, the processor subsystem in modern CPUs consist of your shared L1, L2, L3, shared L3 caches and L1, L2 caches belonging to individual cores. So here we can see that this particular processor has 4 cores, and what it is going to do is through this memory controller interact with your CPU subsystem or your DRAM subsystem. The CPU subsystem or the processor subsystem will interact with your main memory or your DRAM subsystem. So here what you can see is I have drawn few of the signal interfaces that are used for the communication between the memory controller, which is present in the processor, with the motherboard or the DIMMs that constitute the DRAM subsystem. But you have to remember that I have only indicated one of the channels. So the top of the hierarchy is this concept of channel. Remember what channel was? Channel was these, you can say lanes in an highway. Independent lanes that the processor subsystem can use to access data from the main memory. So I have just drawn here the signals corresponding to one channel, but you can just understand that there can be a multiplication of these signals and therefore a multiplication of these channels. So basically multiple channels for having more parallelism is definitely possible, okay, and desirable, especially for high throughput requirements. So what are the different signals that are used to communicate between the memory controller to the DRAM subsystem or the main memory? It is first, obviously, there should be an address bus, and there should be a data bus. Just recall that this is a good recap of our von Neumann architecture as well. Remember, even in the von Neumann architecture, we had broadly classified that the von Neumann architecture consists of logic and memory elements which are spatially separate. We just see another implementation of the von Neumann architecture over here. So the address bus consists of 3 main components because it is supposed to bring out data from from memory locations which require 3 different aspects of address. The first is definitely the row and the column address. So as you know, the address bus will go and reach each and every memory array, and from every memory array, like we discussed in the last class, only one bit gets selected. So what is the corresponding row or the column from which that one bit will come out from each memory array is indicated by this row and column address. Also, we saw that at a time, only one bank is being used. Why only one bank is being used? Remember the concept of doing interleaving. While other banks are being refreshed, one bank is available for access. And so at a time, only one bank data from one bank is being brought out in one clock cycle. Okay. So bank address also, which is a 3-bit address, is an important part of your address bus. Why is it 3 buses? Why is the bank address worth 3 bits? It is very simple. This is because each chip, as we have seen in the last time, consists of 8 banks. So 2 to the power of 3 is equal to 8. So the bank address must consist of 3 bits. So here we have around 14 bits dedicated to row, 10 bits to the column, and the bank address consists of 3 bits. Okay, so this is one very important aspect. The second important aspect is the data bus. So data bus, here I have assumed a generic modern day CPU. As we know, most of our modern day CPUs have a word length of 64. So the data that will be read into the processor subsystem, or which will be written through the memory controller into the memory subsystem, is at a time will be of a length of 64 bits. Okay, 64 bits or 8 bytes. Okay, so other important signals are called the control signals. So the control signals consist of read enable, write enable, then column strobe, row strobe, so on and so forth. So these are basically control signals which are asserted from the memory controller, which gives information to the DRAM subsystem or the main memory subsystem about what is the operation that is to be instructed or desirous from the processor subsystem. Okay, so all of this control is exerted by the memory controller sitting inside the processor subsystem. The last important signal, which is just 1-bit signal, is called chip select. Chip select. So what is the chip select? It selects what is the rank. What is the rank from which you want the data to come out of, or which rank 0 or 1, into which you want to write data into. And this brings us to the second important part of our hierarchy, which is the dual inline memory module. So remember, the dual inline memory module is that green color printed circuit board which we buy from Amazon or from some vendor, and we place it in the motherboard of our CPU subsystem. Okay, a motherboard of our PC, rather, of our personal computer. So as we had seen, it is called dual inline memory module because it has 2 sides, physically 2 sides. On one side, you have 8 chips. One side consists of 8 chips, and the other side, the back side, consists also of 8 chips. So the front side, the chips which are constituting of the front side, are generally given the rank of 0, and that of the back side are given the designation of rank 1. And this chip select, which is 1 bit, actually selects which is the rank to be selected in the dual inline memory module. Now, common sense would suggest if there are more than 2 ranks, rank 0 and rank 1, if you have 4 ranks or 8 ranks, 4 ranks is also used in server chips, the number of bits that the memory controller has to give out as chip select will just keep increasing. If it's 4 ranks, the chip select will not have just 1 bit, but it will have 2 bits, because 2 to the power of 2 is 4. Okay, so this is the essential communication between the CPU subsystem, which is transacting with the dual inline memory module, which constitutes of the 2 ranks through one of the channels. Okay, next we go to the next hierarchy below rank. And as we know, we have just discussed that each rank consists of 8 chips. So each rank consists of 8 chips, from chip 0, chip 1, all the way to chip 7. Remember, each chip in turn consisted of 8 banks, right? So each chip in turn consisted of 8 banks. Since there is information coming out of only one bank at a time, each chip gives out data only from one bank consistent of the one of the 8 banks which constitute the chip. Therefore, at a time, each chip gives out only 8 bits of data. And therefore, the 8 chips which constitute one rank will give out 8 into 8, 64 bits of data, which finally goes into or out of the data bus, depending on whether you're doing a read or write operation. Okay. Next, what we saw is the hierarchy below the bank. And below the bank, we saw that every bank constitutes of 8 individual memory arrays. So one bank constitutes of 8 individual memory arrays. And as we saw that in each memory array, the same row and column address is selected. And therefore, from that very location, 8 bits are being extracted out of one memory, out of one bank, right? So it is very important here to note the fact that since the address bus is going to uniformly to all the chips, therefore the same bank in every chip is getting selected. Chip 0, chip 1, all across chip 7. In this case, it happens to be bank 0, bank 1, bank 2. So here, the bank 2 in all the chips are actually getting selected. And within the bank also, within every bank also, the same row and column address is being selected in every array of the bank. Okay. And therefore, as I kind of indicated, from each and every row and column, 1 bit is outputted, and therefore from one bank 8 bits are outputted, and these 8 banks at a time only one bank is selected in the chip. So 8 bits from one chip is being sent out, and collectively from one rank or from one DIMM at a time 64 bits are being sent out in one channel. Okay, so I hope this gives you a good understanding of the DRAM subsystem architecture. And now we are in a very good position to go to the very interesting element right at the bottom of the hierarchy, which is the individual 1T 1C cell. So now we will begin our study of the individual 1T 1C cell, and let's look at its schematic. So the schematic for the individual 1T 1C cell looks very straightforward. So the most important part of this 1T 1C arrangement is, of course, your storage node. The storage node is the intersection between your access transistor and this common node capacitor. Okay, so one side is the common node between the access transistor and the capacitor is known as the storage node. And the storage node is what is the most vital functional part of your 1T 1C cell. This is because the storage node is what stores your logic levels. If the storage node has no charge in it or no voltage on it, it indicates a logic level of 0. If the storage node is charged to VDD, the logic level is considered to be 1. Okay, and the next important aspect are your access transistors, which is an NMOS transistor, which connects the storage node to the bit line. Okay, it connects the storage node to the bit line, and the gate of the access transistor, just like in the SRAM cell, is controlled by the word line. Now, more realistically, the word line is in the plane, inside the plane of the slides or the paper, whereas the bit line is on the plane is in the same plane as the plane of your slide of your paper, right? So the operation is very, very simple. Whenever word line is turned on, whenever word line is asserted, the access transistor gets turned on, and now the storage node is connected to the bit line through this NMOS transistor. Okay, so whatever information is to be read in or read out, is to be read in or written out, is being controlled by the peripheral circuitry. In the read section, of course, the value from the storage node, or the charge from the storage node flows inside the bit line and is read through the sense amplifier. So we will go into details of read and write cycle. Let's just now focus on the cell architecture. So just drawing the schematic of the 1T 1C cell looks very simple. But how is it actually implemented in silicon? When you see how the device is actually fabricated, it will really surprise you. Such a simple structure of just one transistor and one capacitor has this very intricate and very complicated implementation on a fabricated chip. Why is this the case? This is a very interesting question, and we will go into details of why you need to make such a complicated structure. But let's first discuss what this structure is about. As you can see, a better representation of this structure is a bit complicated. So simplified version of the structure I have drawn over here. So if you see, this consists of a very teeny tiny access transistor along with a very large aspect ratio capacitor. So why do you have this very large aspect ratio capacitor is a very interesting story, and that story we will cover, or we will really be able to appreciate when we understand the read operation of the DRAM cell. But right now, let's focus on how this is operating. As you can see, right at the bottom of your screen, or bottom of the schematic, you can see that you have your, let me bring out the highlighter. You can have your cell transistor. Your cell transistor is nothing but your access transistor. So your access transistors are actually very, very teeny tiny compared to the entire SRAM cell. The rest of the SRAM cell consists of the cell capacitor. You see this huge cell capacitor of a very large aspect ratio. By aspect ratio, I mean that the length of the cell capacitor is much larger compared to the width dimensions of the cell capacitor. As I said, we will discuss more in detail why you need to fabricate it in this manner. The next important thing to notice here is what is the position of the bit line and the word line. As you can understand, the bit line will be connected to one of the ends. So if you zoom in, you will see that if you zoom in into this image, you will see that this is the cell transistor. One end of the cell transistor is connected to the bit line. One end of the cell transistor, as you can see over here, yes. So one end is basically connected to the bit line. So one end of your cell access cell transistor is actually connected to your bit line as indicated over here, and the bit line, the information from the bit line of course will go to the outside peripheral circuitry or peripheral transistor, right? So the other end of your access transistor is connected, as you can see, to the storage node. See, other end is connected to the storage node as also indicated in this particular schematic, right? And as a result, you have to understand the bit line is in the same plane as your capacitor and your transistor, but the word line is perpendicular. Why? The word line has to be connected to the gate of the cell. So if you zoom in, you will see that the word line over here is connected to the gate. So the gate of the access transistor is what the word line is connected to. So it is basically a three-dimensional image. The word line, a three-dimensional device, the word line goes inside the plane of the paper, and the bit line is connected in the same plane as your access transistor. Fine. So this is what this very complicated structure of fabricated looks like in the fabricated chip. But the 1T, this is how a simple 1T 1C schematic is translated into a fabricated chip. The next thing that we will study is the most vital operation, which is your memory hold operation. As you know, in the memory hold operation, the philosophy is very simple. The idea is that you need to hold on to the value which is written on the storage node, and to do that, you have to completely disconnect the storage node from the bit line, or you have to decouple the storage node from the bit line. And in order to decouple the storage node from the bit line, what you essentially do is you deassert the word line. And if you deassert the word line, the access transistor will be off, and in an ideal case, this transistor will give you very large resistance or infinite resistance, and therefore the storage node will be completely cut off or will be decoupled from the bit line. However, as you may be able to understand that nothing in life is really ideal. In realistic transistors, there will be significant amount of leakage parts, which will hamper the storage node from being completely cut off from the bit line. Okay, so this realistic transistor causes a lot of leakage paths for the charge which is stored on the storage node to be to slowly dissipate, and therefore it is very important to study what are these leakage paths and if we can possibly control them. Last important aspect when we are discussing about the transistor is when you make the DRAM cells smaller and smaller. A part of making the DRAM cells smaller is to reduce the size of the access transistor as well. But when you start reducing the size of the access transistor, what essentially happens is you start having short channel effect. And if you have done a basic course on semiconductor devices, you would know that these leakage effects are even more prominent when you have short channel transistors. Okay, this is just something to keep in mind, that the leakage paths become even worse when we go to smaller and smaller dimensions. Okay, so it becomes very important to be able to control these leakage paths. Otherwise, you will have to refresh your DRAM at very regular intervals or very short intervals. So this is why studying of the leakage paths is very, very crucial. So in front of you, for simplicity's case, I have placed a planar transistor, planar access transistor, and a simple storage node. Remember, this is not the actual representation on a fabricated chip. We saw in the previous slide, actually the transistor is very small and the storage capacitor is very large. But for the sake of understanding just the leakage paths, it might be more valuable to represent it like this for the time being. So the question that I want to ask you, from your knowledge of semiconductor devices, can you start guessing what would be the leakage paths when the transistor or when the device is in off condition? When it is in off condition, because this is an NMOS, the gate bias or VG will be equal to 0. Whereas the drain bias, we are trying to see the case where leakage will be worse off. So we are considering that the storage node or the drain terminal in this case happens to be VDD is equal to 1. Or basically what you are saying is that you have stored a logic value of 1, or you have the value of the voltage in the storage node is VDD. So under this circumstance, the most critical circumstance, what will be the different paths through which the voltage or the charge in the storage node will start leaking out? So let us try to track them one by one. The first leakage mechanism that one can think of is the PN junction reverse bias leakage. Where is this coming from? Remember, any transistor has N plus and P. So this is an NMOS. So the drain regions will be doped to N plus, whereas the substrate will be P. So there is a PN junction diode between the N plus and the P regions. Now, please see that the voltage on the drain terminal is VDD is equal to 1. Okay, so the N plus region is 1, whereas the P type region or the substrate of the transistor can be generally assumed to be grounded. So under these circumstances, please understand that the PN junction, which is forming due to the N plus drain region and the P substrate region will be reverse biased, right? And as we know that although small, there is always a reverse saturation current in any diode structure. You can call it the reverse saturation current or the leakage current under reverse bias. So this leakage current under reverse bias is what will be the first and one of the important mechanisms through which the charge in the storage node will slowly leak out. Charge will leak out through this reverse saturation current. This is the first mechanism. What is the second mechanism through which there can be leakage currents? The second important mechanism is this very interesting concept called GIDL. GIDL stands for gate induced drain leakage. Gate induced drain leakage. Let me explain what this gate induced drain leakage is. And to do that, I will zoom in to this particular region of the transistor, and that is what I have done in the right hand side of my slides. So remember, the drain bias is roughly 1 volt, the gate bias is 0 volts, and because there is a large electric field in this interface. So what is this interface that I'm talking about? The interface that I'm talking about is the interface between the gate metal, the gate oxide, and the edge of this drain N plus region. At the this particular region, there will be very large band bending, as I have indicated in this particular diagram. And this very large band bending will allow for some tunneling to happen from the valence band of the N plus drain region into the conduction band of the P-type region. And this current will then flow through as a leakage component through the gate oxide into the gate terminal. So this gate induced drain leakage happens when there is a large difference in electric fields or large band bending due to large electric fields at the drain and gate oxide terminal. So this is the second most important reason for having leakage that will drain out the charges stored in the storage node. The third important component that one could think of is the subthreshold leakage. So what is the subthreshold leakage? As you know, any transistor at zero gate bias, ideally if it was an ideal switch, it would have zero current. It would have absolute steep subthreshold slope and zero current in the off state, which is at Vg equal to 0. But there are no ideal transistors, so every transistor has a finite subthreshold swing. Subthreshold swing is essentially the slope with which the transistor turns off, goes from the off state to the on state when ID versus VGS is plotted in the log scale. So this results in a finite off current for the N-type transistor. So this finite off current, which flows as a diffusion current from the drain to source, is also responsible for leakage of charges from the storage node. Okay, and the final reason why there can be significant amount of leakage is that all the time we were considering that this capacitor is an ideal capacitor. But as we will see, what we are doing with these capacitors or the storage node capacitors is making the gate oxide thinner and thinner. And the reason for trying to do that is to increase its oxide capacitance. You know, oxide capacitance is inversely proportional to Tox. So smaller the Tox, larger is the oxide capacitance. In a bid to increase the capacitance, what we are essentially doing is we are trying to reduce the oxide capacitance, and therefore it deviates quite significantly from your ideal behavior, and even the capacitor, which is ideally supposed to be an insulator, starts leaking. So this forms the fourth most important aspect, as I have marked over here, which results in the leakage of the charges from the storage node through the parallel capacitor, oxide of the parallel capacitor or insulator of the parallel capacitor into the VCP. VCP is the voltage of the common plate. Okay, so these are the several mechanisms through which there is a leakage of charge from the storage node into the through the transistor and through the capacitor, right? And because there is a significant amount of leakage mechanisms happening in the DRAM device, the charge that was stored on the storage node starts decaying over time. And as a result, it becomes an imperative to keep refreshing the data. So an interesting question would be, how often do you have to refresh the DRAM cell, and what is the mechanism for this refresh? And that is what we will be covering in the next class, along with understanding read and write mechanisms in the DRAM cell. So let us conclude in this class. In the next class, we will look at refresh mechanism, the read and write operation in a DRAM cell. Thank you.